first, I guess, topic is just the homework is due tonight, correct? Any questions or comments about the homework? Or is this under control? Who feels they have it under control? Okay, a few people. Any questions or comments or experiences? Okay, and do that then, I guess, afterwards for the next week is the project proposal stuff. A few people have started talking to me about their project proposals if they want to. Again, I'm available after class. One resource some people have asked me, oh my God, what should a proposal look like? I posted on the website examples of 3 good project proposals from previous years on my website. I think they're linked to from the homework. Well, anyway, if you go to my webpage, there are examples of good proposals from previous years. And so, you may want to use them for inspiration. I think the size of your proposal is less than the size of the ones that I had them do. The page limit is a little bit less, but you'll still see kind of what a good proposal looks like. Any questions about that or anything? Okay, so today I'd like to talk about give a review of linear algebra. And this, some of people may not be enthusiastic about because you've probably had linear algebra in high school. But in some sense, there's a lot of what is, classically data science kind of reduces to things that you do on data matrices, where typically you have rows for examples and columns for, features. On your project, many of your projects will involve building data matrices and then trying to analyze them. Linear algebra is kind of the mathematics of matrices, and that's why we're going to be talking about it a little bit. I know you've had an undergrad course in it. Okay, some of you that may have been a long time ago. And we're going to talk in the next couple of lectures about some linear, various machine learning algorithms that are kind of based on, essentially linear algebra. And that's why I feel kind of a need to review it. Okay? Any questions about that? Okay. So what are matrices? Well, what can you do? What can an n by m matrix represent? We've seen n by m matrices in many times in this class so far. We've talked about, again, typically data matrices, feature matrices. You have rows being objects, columns being features. We've talked about geometric point sets for clustering. Those are ones where, again, we have rows or points, the columns are dimensions. We've talked about, we haven't really talked about, but certainly you're familiar with matrices being representing systems of equations. Here you've got a row, every row is an equation. Every column is the coefficient of a particular variable. We've talked about, certainly we've talked about, and we'll talk a little more about graphs and networks. Typically the way to represent a network is as an if you have n vertices, is an n by n matrix, where element mij is the number of edges from vertex I to j. Okay? And finally, of course, we talk about vectors in here. Any row or column of a matrix can be interpreted as a vector. Any questions? This I know you know. Now, when you look at a linear algebra, one of the reasons why linear algebra is a great thing is that you can often write very, very concise formulas on matrices that have, a surprising amount of power. So for example, does anyone know what this formula on the bottom is? I have on my screen a formula. Does anybody know what that is? Okay. Let me tell you, you have used this formula this semester. What is it? Okay. That happens to be linear regression. Okay. That when you what is the situation? Let's think how we would interpret this as a linear regression. In linear regression, what is the situation? You've got a bunch of points and you've got a target variable, right? The points here are going to be given by the matrix A. The target variable will be given by the vector B. So you kind of are going to have some linear function of each row is going to be the corresponding B value. Okay? And W is the weights on the columns. Okay? The weights on the features that will, produce the best fit to the, to the underlying points. Okay? And what is that formula here? Well, it takes the data matrix, you multiply it by its transpose, you take the inverse of it, multiply it by the transpose, and multiply it by the target value, and you get the weights. Okay? Any questions about that? When I see something like this, I find it amazing, and I find it that I don't have much intuition about this. Does anybody have any intuition as to why this is the linear regression? Okay, you didn't recognize it in a police gallery before, so in a police lineup. Okay, but so what do I think about linear algebra and, at least with my level of understanding? It's clear that linear algebra formulas provide, compact ways to represent amazingly complicated things. Okay? Now, I personally find it very difficult to understand or interpret these things. I don't know if you're like me or not. So there should be some level of respect. You may say, well, this thing is just going to come out of some algebraic derivation. That's where those formulas came from in linear algebra. I will confess that although I am an algorithm theory person, I know a fair amount of mathematics. Okay? I find algebraic proofs, sequences of algebraic statements, very, unsatisfying proofs generally. Has anyone ever seen a proof that 2 equals 1? Okay? How many people, did everyone see this thing? At the end, we have proven 2 equals 1. Why is 2 equal to 1? Or why is, I don't think people here believe 2 equals 1. What's wrong with this algebraic proof? Every statement looks fine. Yeah?
There's a step, the fourth step, where a minus b is mentioned, and then you divide a minus b on both sides.
So what am I doing? So again, if you work through this, if a equals b, we can certainly multiply both sides by a. We can certainly subtract a b squared term. We can certainly factor both sides. Now you're saying when we cancel from a minus b and a minus b, we get a plus b. Okay? And here's the ding, 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 right? What's wrong with this? Okay, the problem here is, if a is equal to b, what is a minus b? 0. Dividing by 0 is a bad thing, right? So this is, this is one of the reasons why I find algebraic proofs kind of unsatisfying. Because it looks basically right. There isn't any real intuition to what's being done here. But there is still a logic that is kind of slipped in here that is mysterious, okay? I tend to like combinatorial proofs or combinatorial arguments, bijections, things like this, because I kind of have a better intuition about them. But what can we learn from that, the proof that 2 equals 1? One is, I think that the proofs that, to me at least, the proofs that are based on algebraic definitions generally don't carry intuition. Okay? There is often a problem with special cases. And the special cases when we do normal algebra was typically dividing by 0. In linear algebra, we're going to see that there are other special cases. We're going to have things like there are matrices that are singular, okay, or non-invertible, okay? So if we go back to here, when is linear algebra, when is, linear regression not going to work? Okay, this is a formula for linear regression. When is this not going to work? Okay. Since some matrices are not invertible, there's a quiet error case here, where if your matrix is not invertible, this doesn't work. Okay, and so this is one thing that you got to be aware of when you're dealing with using linear algebra methods in data science. Any questions about that? Okay, now in many of our data sets, our data elements are represented as rows in a matrix. Rows in a matrix can be thought of as points in a d-dimensional space. One way to think about a point in d-dimensional space is if you take the origin point and any point, that's going to define a line or an array or a vector, okay? Sometimes it's good to interpret your points as vectors, okay, which are kind of going to be unit vectors, okay, vectors of length 1, plus their magnitude, okay? Why is this a useful thing? Because for a couple of different reasons. One, we're often faced with the problem of trying to tell the similarity between different things, okay? And, kind of the normalization that comes from taking a point and reducing it to a unit vector often makes it easier to compare things because all the points become comparable. So one kind of a vector, for example, that will come up in maybe old-fashioned natural language processing might have been if you wanted to classify a document that was by the count of what kind of words in it. How many times does it mention football? How many times does it mention cats? How many times does it mention dogs? If you treat it as a vector of counts, a matrix, an array of counts as your feature vector for each word, then, if you wanted to compare an article about something to a book about something, okay, the book is going to be a point way out here because the number of words is just very large in a book, okay? If you really want to tell whether two articles are about the same thing, it's often better to compare the scaled unit vector, okay? Any questions? Now, what is the best way to compare the similarity, or a useful way to compare the similarity of two vectors? Well, there is, it is the case that if you have two vectors defined by, again, points, you have an origin, an angle at an origin, and 2 points. If you want to measure the angle between the 2 points, okay, the cosine of that angle is going to be the dot product of those 2 vectors divided by the size of the vectors, okay? The size of the vector is, the Euclidean distance, essentially, between the origin and that point. If they are unit vectors, then the length of A and the length of B are both going to be 1, okay? And it's just going to reduce to a dot product. But what's interesting about when we think about the angle between two vectors, okay? If these vectors kind of represent points in feature space, okay, well, when the angle is small, that is a measure that the two vectors are very close to each other. And if we interpret the cosine of an angle, what is the cosine of the angle when the two vectors, when the angle is 0? 1, okay? That's like a correlation. A correlation is between -1 and 1. A cosine is between -1 and 1. When is the angle going to be, when is the cosine of theta equal to -1? When it is basically pi radians apart, okay? And the cosine is going to be 0 when they are pi over 2, 90 degrees apart. What is the interpretation of that? A small angle corresponds to something like a high correlation. A very negative, cosine corresponds to something like a inversely correlated, okay? And an angle of pi over 2 is interpreted as being that the vector means that the vectors are orthogonal, meaning there's no relationship between the 2 points. Any questions about that? So the good thing is this cosine formula generalizes to higher dimensions, and so the dot product, kind of we think of as cosine similarity, okay, gives us a good way to measure this similarity of two vectors. Any questions? Okay, where does this come from? Okay, why is it that the dot product of the two vectors is equal to the cosine of the angle? Okay, again, the way that you would do this is one of those algebraic proofs that I don't like. Okay, how would you argue that? Suppose we have two vectors, A and B, defined by the points x1, 1, y1, and x2, y2. Okay? If they are unit vectors, okay, well, actually, forget whether they're unit vectors, okay? If, what do we call it here? There is an angle defined, okay, between the origin and each of these points, and the point is given by the x-coordinate is the cosine times the angle, the y-coordinate is the sine times the angle, the sine times the length. These are length, not angle. The coordinates of our points, if we know what the angle is between them, are A and B, okay, those are going to be where the points are, and theta is the difference between the angles. That's the angles between the 2 points. What do we know? The dot product of x times y is going to be A cosine B alpha times B cosine theta, plus A sine theta alpha times B times sine beta. There is a trigonometric identity that says that cosine of A plus B is equal to the cosine of A times the cosine of B minus cosine A times sine B. Okay? We can then replace this and it becomes the cosine of B minus A, and that's exactly the angle between them. Okay? Any questions about that? Okay? So this is a proof that in fact the dot product does correspond to the cosine. It doesn't give me any real intuition about it, okay? But these things do come from someplace. Any questions? Okay, good. Now, for the rest of the lecture, I'm going to talk about operations on matrices. And to visualize them, I find it's useful to have a matrix I can look at a picture of. Okay? So here are two matrices of things. What's the thing on the left? Does anyone know who this guy is? Abraham Lincoln. And who is this guy? Who's on the right? What's on the right? This is the Lincoln Memorial. Again, he was a great president. For a great president, we give them a memorial. Okay? Any questions about that? So now let's interpret these images as square matrices, and we will work on them and see what happens when we do matrix operations on these things. Okay? So the first matrix operation was, we talked about transpose. What does transpose mean? Okay? Transpose is the art of turning an A by B matrix into a B by A matrix. Okay? And basically it's about reversing the coordinates here. Okay? The transpose element of ij is going to be exactly equal to the element ji in the original one. Any questions about that? Okay? Now, we talked about dot products. Dot products, remember, were kind of a dimensional wide product. Okay, we were going to take a vector, here let's say a 3-element vector times another 3-element vector. The dot product was basically the sum of the ith value of one times the ith value of the other. Okay? So the dot product was going to measure, in this case was going to be 1 times 7 plus 2 times 9 plus 3 times 33. Okay? If we're going to have dot products, okay, the points have to have the same dimension. Okay, so you're multiplying a k-element vector by a k-element vector. When we talk about matrix multiplication, what we are talking about is an x times y matrix by a y times z matrix. And for each element, we are going to compute the dot product of the ith row times the jth column. That's what's going to be the ijth value of the product. Okay? Any questions? So matrix multiplication is a common thing that you've seen. Okay? And as we've seen, if each value is a dot product, and the dot product kind of measures the similarity, each element in the product of a matrix measures in some sense how in sync the row and the column actually are. Okay? Any questions? We'll see that in a minute. What are the properties of matrix multiplication? It is not commutative. If you put the matrices in a different order, you multiply them, you get the same answer. It is associative, so you can group these things however you wish. Okay? And there is an identity that you can multiply each matrix by that leaves the, the original matrix. Okay? The algorithm that you learned in high school computed basically x times z dot products, each of which took y time to compute. So that was an x times y times z algorithm. Okay? But in the libraries, it pays to use matrix multiplication libraries because they are highly optimized for performance and numerical stability. Okay? Fair enough. Now, what happens when you take a data matrix and multiply it by its transpose? We saw multiplying something by its transpose in the linear regression formula. Okay? if we have an n by d data matrix, n elements by d dimensions, what do we get when we multiply n by A by its transpose? The transpose, it was n by d times d by n. So we're going to get an n by n product. And each dot product is going to do what? It's going to compare a row of the original matrix times a column of the transpose, which is a row of the original matrix, right? So when we compute A times A dot, we're going to get a measure of, in some sense, how in sync each row is compared with each other row, okay? If you think of it, if you have, by in sync, if you have a big value times a big value, you get a big contribution, okay? What happens if you get the transpose of A times the transpose times A, okay? This is going to be a D by N matrix times a N by D matrix. You're going to get a D by D matrix of how in sync are the columns of each matrix. Okay? Any questions about that? These things we call covariance matrices because they capture a lot of the structure in what's going to happen in a matrix. So now take a look at this. Okay? This was our Lincoln Memorial image. What is the covariance matrix look like when we have A times A transpose? This is measuring how in sync the rows are, right? And what do we get here? For this band of rows, this band of columns is very heavily in sync with each other, right? You get large dot products, right? And why is that? It's basically because every one of these, every one of these rows looks very similar to each other. Now, do every one of these rows look very similar to each other? Down by the steps, they also look similar to each other, right? What is the what is the part of the covariance matrix that deals with these steps? It's basically out here. Does everybody see that? Why is it that this area is much lighter than this area, if all of these steps are also very much in sync with each other? Okay. Note that this thing has darker values. This has bigger values, right? The dot product is going to be larger. The dot product by itself is an unnormalized thing. Does everybody agree? So this has meant that these two were in sync with the interpretation is these were all in sync with very, very heavy rows. These are lighter rows with smaller numbers that were also in sync. What does the column-oriented covariance matrix look like? When are two columns in sync with each other? Okay? And in this case, what do you see? Why do we get a checkerboard like this? It's because whenever we have a column that goes through a column, okay, it's very, very light. Does everybody see that? And that these two, any pair of columns that go through columns are going to be highly in sync, but they're going to include light values. For the darker ones, okay, for the area between the columns, they're going to be in sync, but with darker values, so that's why we get the dark squares there. Any questions about that? Okay? So the covariance matrix captures a lot of what's going on in here. Now, is the covariance matrix symmetric? Why is the covariance matrix here? These things look pretty symmetric. What does symmetric mean? It means that they, you know, if you cut them along the main diagonal, they would reflect. Why is it symmetric? Because the dot product of the column I and column J is the same as column J with column I, right? Okay, good. Now there are other things that matrix multiplication is good for that has interesting interpretations. One that I find useful to know about and surprising is, suppose you have a graph which is represented by an adjacency matrix. Okay? So edge ij is going to be 1 if there is an edge from vertex I to j. It's going to be 0 if there is a no edge between I and j, right? What happens if you multiply the adjacency matrix by itself? Essentially square the adjacency matrix. What is the value of ij going to be? Okay? Does everybody get that? You've got the original adjacency matrix of the graph. You square it. What is the square of an adjacency matrix? Anybody see that? Well, what happens when aik is going to be non-zero? Okay? Suppose we have a matrix, the adjacency matrix. Suppose the product, okay, of what you call it, in the product of matrix A times matrix A. Suppose ik is equal to non-zero. If it's equal to 1, if it's going to be the product of A times itself, in order to get a non-zero term, there had to be a j, okay, such that there is an edge aj and there is an edge jk. If that's true, then what does this mean? If there's an edge from I to j and from j to k, that means that there is a path of length 2 between the two vertices. Does everybody agree with that? So if you take a matrix and square it, the product matrix is going to be the count of the number of paths of length 2. Okay? And again, if you cube it, it's higher, and so on. Okay? Any questions about that? Okay? So there's a lot of interpretations of matrix multiplication. Okay? You can use it to rearrange the columns of the rows and columns of a matrix by multiplying it by a so-called permutation matrix. You can use it to calculate what the rotations are. If you have an image and you rotate an image, where do the points go? Okay? That's also basically another matrix multiplication problem. So multiplying something by the right matrix can have magic properties. That's one reason we care about matrix multiplication. Any questions about matrix multiplication? Okay, if you can multiply matrices, the inverse operation for multiplication is division. Okay? And you don't really talk very much about division of matrices, but people do talk about matrix inversion. Okay? What does it mean when you say that A times its inverse? An inverse, a multiplicative inverse, is something that when you multiply A by, gives you the identity matrix. Okay? Now, A times its inverse equaling the identity matrix can be thought of as saying that the inverse if we multiply both sides by 1 over A, is really the identity element over A. Okay? So matrix inversion is really what plays the role of division when we come to matrices. Any questions about that? Okay? Good. Now, what is inversion? Okay? I know you saw this back in high school. But how do we do inversion? For small matrices, okay, the inverse of a matrix is well known and there's a formula for it. Okay? That kind of the inverse of A times B is going to be, I guess, you know, what you call it. Turns out to be, you know, representable by this formula. Okay? What does this formula tell you about when the inverse is not well defined? Okay? If the formula for, if a 2 by 2 matrix, if this is the inverse formula for it, when is the inverse not well defined? Yeah? When the products of the diagonals are the same, then basically you're going to be dividing by 0, right? So this is a proof that not all, if you believe this formula, this is a proof that not all matrices have inverses, okay? If a matrix in general does have an inverse, it can be solved by using Gaussian elimination. You did this in high school, okay? You took a matrix and you wanted to know, what do I multiply this matrix by in order to get it to the corresponding identity matrix, which has 1s on the diagonals? By going through the, you know, the system of linear algebra, you go through Gaussian elimination, you would be able to solve what was for basically what is the identity matrix of the thing. These sequence of row and column operations basically define the matrix that is going to be the inverse, because it's going to be what took this to the identity matrix, and that is defined by what was carried along. Okay? So if we need to find an inverse, we can do it if we remember how to do Gaussian elimination. Any questions? Now, what does the inverse of a matrix look like? Okay, this is Lincoln. Okay, you guys recognized him. Which president is the inverse of Lincoln? Okay, well, we're not going to go there. Okay, but what does the inverse of Lincoln's picture look like? Okay, it looks like sort of like random numbers to me, right? I guess I don't really know what it's supposed to look like. But what's the important property? When you take Lincoln and you multiply him by his inverse, you get a picture like this. Okay? What is the important part of the picture? You've got a strong main diagonal, because that's what the identity matrix is. Any questions about that? What are these columns you see when you multiply a matrix times its inverse? Why do we see a striped pattern of columns here? Can anybody take a guess? Okay. The answer is, this is numerical imprecision that you see coming up here. Okay? When you're working out an exact inverse, you're getting a long, numerical thing. In fact, there are numerical errors, and that's what kind of shows up when you multiply, a bounded size numbers times a bounded size numbers in real arithmetic. That's kind of what you get there. Any questions? Okay. So anyway, matrix inversion, as we have seen, kind of plays the role of division, and it, kind of, because and it also can kind of be thought of as equivalent to solving systems of linear equations. Okay? If we want to say that x, our data variable times the values of the variables equals our target, solving a linear system, okay, would be equivalent to pulling out what the values of x's are that make that equal. If we multiply both sides by the inverse, basically we solve an inverse, and a matrix multiplication solves the linear system. Any questions? Okay. When it comes to matrices, okay, we've seen that matrices sometimes are not invertible. Okay, a matrix that is not invertible, okay, is in some sense, typically it's because the set of, let's say, equations or the set of rows can be expressed as linear combinations of each other. Okay, there is something called a quantity called the rank of a matrix. Okay, which is a measure of how many linearly independent rows there are. Okay, and for a matrix to be invertible and to have all nice properties, the rank of a matrix should be, of an n by n matrix, should be n. If not, we don't really have n different kind of examples, n different things. Some depend on each other. Any questions? Now, what happened? Which one of these matrices, if we go back to this thing, let's look quickly at Lincoln for a second. Which one of these matrices looks like some rows on it are more likely to be linearly dependent on each other than others? Okay? Or if we take a look at these things, do the rows, if I told you one of these matrices was not a full rank matrix, which one would it be? The one on the right, right? Does everybody kind of see that on this one you've got a large number of rows that really look a lot alike, okay? And so when we in fact computed on my Lincoln, the rank of that matrix, it was a 512 by 512 matrix. The rank of the memorial came out to be less than, okay, the matrix, okay? So if I tried to invert the Lincoln memorial, it would have crashed, right? How do you deal with a matrix when it's low rank, sufficiently low rank that you try to do a matrix operation and it doesn't work? One kludgy idea is to add some random noise to the elements of the matrix. If you add a little bit of random noise, suddenly the matrix gets full ranked, and numerically you can do the things that you want to do, okay? And if you added a small enough amount of noise, it hopefully doesn't mess up the matrix very much. Any questions? Okay. When it comes to many machine learning algorithms, okay, they are going to be, it turns out, can be thought of in terms of matrix factorization. Okay? Suppose I have an n by m feature matrix, okay, where I could express that matrix as a product of B times C, okay, where the internal dimension is going to be some value k. If my data matrix is equal to the product of an n by k matrix times a k by m matrix, okay, if k is small, then I have compressed my matrix. Okay, I get away with a lot less parameters. Okay? And these matrices have a logical interpretation in terms of the features of these things. Suppose we have, for example, a word document by vocabulary word matrix. Here again, we've got for every row, it is a document. For every column, it is a vocabulary word. Football, okay, president, cat, dog, okay? What is going to happen if I take my big document by word matrix and I factor it into two matrices, one of which is a document by K matrix and one of which is a K by vocabulary word matrix? Okay? If I could do this factoring where K is very small, or relatively small relative to N, this is a really great thing. Why? Because this first matrix B is kind of now a concise representation of the document. Okay? Before, each document was a point in n-dimensional space. Now, after I've done this factorization, this document is now a point in k-dimensional space, where k is much less, right? So if I want to compare the similarity of documents, this would be a good thing to do, right? Now, what is this going to be? This is going to be a k by the number of words matrix, right? And what happens if I do that? Well, now for every word, I've got a short feature representation. One would like to think that if this is true, similar words would have similar, in this case, columns, okay? And so this is, if you can take a matrix that is document by word or example by features, okay? This gives you a way to construct kind of more concise representations if you can do the factoring, okay? And these are kind of useful. Any questions? This is the principle by which many of the embeddings that we would come up with. In your homework, you were doing feature embeddings from images and from text, okay? In principle, these kind of embeddings could come out as a product of factoring such a matrix. Any questions? So the good thing is that if we can factor matrices, we can get more concise feature vectors, okay? If we can't factor, but factoring matrices precisely is not always well defined. But there are algorithms that will try to approximately factor matrices. And this is what is kind of used to kind of build a lot of these kind of compressed feature representations. Any questions? Okay. So what do we know about factoring matrices from when we were in high school? Okay. When I was in high school, I learned about a specific form of matrix factorization called LU decomposition. I suspect you guys did too. Okay. This is something L and U stood for lower and upper matrices. Okay. These are useful for turning, solving linear systems of equations. Okay. And when you did one of these LU factorizations, there were all kinds of different properties. Okay. One is that the main diagonal, okay, of the U matrix gave us the determinant. The determinant was a number that if it was 0 meant that the thing was not full rank. So determinants are kind of useful things. What happens when you do the LU decomposition of a matrix. Here on the right is my matrix. Here on the left is the LU decomposition. L and U represented triangular matrices, right? If you had two triangular matrices, okay, you could fit them in one image. So this was the lower matrix, this was the higher matrix. L times U reconstructed this. Which image did I do the LU decomposition on? Lincoln or the Memorial? I think it's pretty clear the Memorial. Why, when I multiplied L by U, does the matrix look so weird? You can tell it's the Lincoln Memorial. But why isn't it in the right order? Okay? Remember, for LU decomposition, it's usually used for solving systems of equations, right? And what happens to a system of inequations if you permute two of the rows? Nothing. It just rearranges the equation, right? And basically, LU solvers happen to, for numerical reasons and simplicity, okay, permute the rows of the equations as they solve them, because that's not so important. But again, the product along this main diagonal would have given us the determinant. Any questions? So LU decomposition is a matrix that you know how to factor. There's some kinds of things you know how to factor, some things you don't. Any questions? Okay. The other part of linear algebra that you probably covered in your class were eigenvalues and eigenvectors. And these have some use to us. What is the interesting thing about this example? Here I've got a matrix. I am multiplying it by a vector. And what I get is the same thing as a number times a vector. Here I have a matrix. I multiply it by a vector. And I get the same thing as a number by that vector, right? This is my matrix times a vector is equal to a constant times that vector, right? So this is the important equation in eigenvalues and eigenvectors. A times V is equal to lambda times V, okay? Now, what's interesting about this, okay? In this case, we're saying that this vector is so powerful that this vector and that constant tells you something about that matrix, okay? In some sense, okay, multiplying this vector times this whole matrix has the same effect as multiplying a constant times that vector. So this vector and constant tells you, in some sense, contains as much information or a lot of information about that matrix. Okay? And so these pairs of vector and scalar pairs, okay, they each tell us a lot about the matrix, and together the complete set will tell us everything about the matrix. Now, I'm going to refer you to a video if you want when you get home. You can read this. This video does a pretty good job of trying to capture what is going on, try to provide some intuition about what eigenvalues and eigenvectors are doing. So I kind of do recommend that. But what's interesting about this to us? Okay? Given a matrix, we can find out what the eigenvalues are of that matrix. It turns out that you can do it by basically taking the determinant of a matrix plus minus some constant, some variable lambda times I, the identity matrix, you get an equation that when you factor this equation, every root of this equation is going to be an eigenvalue. Okay? So given a matrix, with this procedure you can find all the eigenvalues. Okay? There are faster ways to do it to find the largest eigenvalues, which we'll talk about soon, because those are the most important. What's interesting about eigenvectors and eigenvalues? Well, first, any matrix of full rank has n vector value pairs. Each pair of vectors, okay, from a when you start from a symmetric matrix, every pair of eigenvectors you get are mutually orthogonal. This means that their dot product is 0. Okay? That's what orthogonal means in vector world. Again, from the example we had before, there were two eigenvectors, 2 minus 1 and 1 times 2. The dot product was 2 plus minus 2, or 0. Okay? What's interesting about these vectors is the fact that every pair of them are mutually orthogonal. This has the property then that the eigenvectors kind of play the same role as axes in an n-dimensional space. Okay? You can kind of think of these eigenvectors and values as some kind of a rotation of the axes, okay, in a particular direction, so as to best kind of fit the matrix. Okay? And and we can find these vectors and values by solving systems of equations. Okay? Any questions? Now, there are faster ways to find eigenvectors by kind of iterative. Again, you could do them by solving. In high school, you learn to do it by solving the characteristic equation. A times the vector is equal to lambda times the vector. Another way to think about that, though, is that if we take this and multiply both sides by 1 over lambda, lambda being a constant, the eigenvalue, in some sense you get an equation where V is defined in terms of V. One approach that people use to find eigenvectors is you start with a random choice or a guess, okay? Multiply that by A, divide it by the eigenvalue, you get a new vector. And if you keep feeding it back into itself, this is something that converges, okay, under the right conditions on what the eigenvector is. So there's ways of computing it. Any questions? Now, why do we care about eigenvectors? This is where we're going to start to get into the data compression properties of matrix factorization. Okay? Any n by n symmetric matrix can be decomposed into, okay, the sum of, for every eigenvector, every one of the n eigenvector value vector pairs, of the eigenvalue times the vector times the transpose. What is an eigenvalue vector? What is the shape of dimensions of an eigenvector? If you have an n by n matrix, what is an eigenvector going to be? 1 by n, right? What happens if you take an n by 1 times a transpose 1 by n thing? What do you get? N by n thing. Does everybody see that? So one eigenvector interpreted as a, by multiplied by its transpose, gives us something of the shape of the original matrix. And if we multiply it by our eigenvalue, we're going to get a matrix, of some magnitude. And it should be clear that the larger value, that for a larger eigenvalue, it's going to be, give you a larger, larger numbers in that n by n matrix you get by the vector times the vector. So what is it the case? The matrix can be defined as being the sum of these n different matrices, each of which came from one eigenvalue eigenvector pair. The larger ones corresponding to the larger eigenvalues are presumably going to have a bigger part in representing what that matrix is. Okay? And so this gives us a way to start to think about compressing the matrix. If instead of summing up over all n products, we sum up over the k most important of these eigenvalue eigenvector pairs, certainly as k gets larger and larger, we're going to get a closer approximation to our target matrix. But if we add them up from the largest, most important part to the least important part, after summing up a small number of these, we will have a relatively good approximation to our target matrix. And so if we instead sum up after only the, the largest, take the k largest eigenvectors, okay, the k largest eigenvalues and their corresponding eigenvectors, we end up getting a reasonable approximation of what the matrix is. This is kind of the error matrix that we get when we try to reconstruct the covariance matrix of the Lincoln Memorial, you saw that before, using only one, the largest eigenvalue eigenvector pair. By the time we got to 5 of them, this is showing the error. You'll see the error has gone down considerably. By the time we use 50 of them, it's almost, except for, there's very, very little error left in the approximation. So as a dimension reduction scheme, taking the most important of the products, okay, is what gives us a, basically a way to compress the matrices. Instead of an n by n matrix, we will consider an n by k matrix corresponding to the k largest eigenvectors. Any questions about that? Okay, good. Now, there's a technique that is in some sense even better than using eigenvalues, eigenvector decomposition, or at least more general, is this idea of singular value decomposition. This is what you guys are doing on the homework. What is the idea here? The singular value decomposition of an n by m matrix is a specific way of factoring it into an n by, I believe it is n matrix, times an n by d matrix, n by m matrix, times an m, okay, this is n by n, this is n by d, m, and this is going to be, let me say this again. N by n times n by n times n by m. Okay? If we do that, we can multiply this thing out. Okay? Now, what's interesting about that? Okay? it turns out that the singular value decomposition is a factorization where m is brought into this n by n times n by n times m matrix. Okay? The interesting thing about it is that the center matrix D is going to be a diagonal matrix. It's going to be like our eigenvalue matrix. It's going to be a weight for each row. One, just along the main diagonal, a weight for each row. N times this diagonal, U times this diagonal matrix, okay, weighs each one of these diagonals by its importance. D is, this D thing is the importance of the rows in this U composition. Okay? And so, and similarly, you could have interpreted D times V. Okay? It's going to tell you which is the row, column, and column that is most important. Just as in the eigenvalue case, okay, if we retain only the most important rows and columns, okay, we will be able to compress the matrix, okay, represent it with a smaller number of values such that there is relatively little loss. And this is what you are hopefully finding on your assignment. Okay? Yes?
So for the assignment, were we meant to use like either PCA or SVD, or do you want us to use both?
Whichever you want. There's not really a big difference between them. Okay? That's, I think there's just only a difference of a normalization between the two of them. But what's the way to look at it? Okay? For every, you have a, when you did that factorization, there was a U matrix, there was a V matrix. Okay? D matrix was going to tell you which were the most important of the rows and columns to be worried about. This is what happens when we take the, the rows and columns of, I believe this is the Lincoln Memorial. I'm not 100% sure, but I want to interpret it this way. Here, we started out before with a 512 by 512 matrix. We factored it and we kept the first up to 50 rows and columns of the two corresponding matrices. Okay? When we take the product of this row times this column times the transpose of this row, with this column, times the transpose of this column, we take this column, the ith column here, times the transpose of the ith column here, multiplying that, we're going to get an n by n matrix. Okay? These are the 50 most important, okay, columns, okay, that we get. When you look at this, these are where they're going in increasing order. What do you see as you look for the small, the highest, the lowest value rank, meaning the most important singular value vectors? What does it look like? Do you see anything as you move from the most important, okay, feature values to the less important feature values? Do you see anything when you look at those? What is the thing that you see? Yeah? You're saying more noise or more detail. Okay, that's the way you would say noise. Okay, I would say more detail here. Why is that? It's because if you were going to try to reconstruct it from only one of these things, you want to rough out what the image is like, right? And so in this particular case, you see that gradually it got more, you say noisy because it's filling in more detail. What happens when you use something like singular value decomposition? As you add more and more of these row times transpose, column times transpose column matrices to the total, the error declines, but it declines very quickly. So after a relatively small number of these features, you reconstruct most of what the detail is in the image. So this is what happened when I took the Lincoln face, okay, and I reconstructed, it was a 512 by 512 image. This is what you got when you used only 5 sets of singular values. By the time you got to 50, it's certainly visually the same as the original image. Okay? And even with only 5, you could pick this guy out on a police lineup. Okay? So it's sort of an idea that, again, if it should be the case that by taking the SVD, you should be able, if you can reconstruct a lot of the values that you have there, okay, you should be able to, basically get a good approximation. And something from a small number of features will do what you want. Okay? Any questions? Any experiences that people had on the using the SVD on here? Okay. This is all I am prepared to say for today. So I know I've let you run late a couple of times. I think I'm going to take back these points here. Any questions about linear algebra or anything like this, or any of these things? Okay? It's good to have it as the basic vocabulary. For the next couple of classes, we're going to talk about where the linear regression formula and similar linear models come from, okay, and how we solve them. Okay, any questions? If not, thanks for your attention. Good luck on the homework. And anyone who wants to talk to me about the project, we can talk about it. Okay, thank you.